Greetings, chemists. This video is going to be one in which we examine how scientists excite the electrons in an atom and then use that light to give us information about the nature of that atom. Okay? And we're going to start off by talking about what is light, and so we have an understanding of light so that we can then use that to talk about atoms. So, at its fundamental, light is a wave. And let's start with a wave you're probably familiar with. Suppose you threw a rock into a pond and you saw ripples going outwards from where the rock landed that traveled like this. So those are waves. Those are the molecules of water inside the pond are vibrating up and down because they got hit with the rock. And then they also propagate. We say they propagate outward. The ripples travel outward. The water doesn't necessarily travel outward, but the ripples do. Okay, light is a similar phenomenon where we get an electron to vibrate back and forth, which is what we're going to be examining, the vibrating of electrons. And when it does that, it causes ripples, not in molecules the way the rock did with the water, but in this invisible substance that we're going to call the electromagnetic field. So light is a vibration in the electromagnetic field. Now that's a whole other deep rabbit hole in physics about what is the electromagnetic field and field theory, etc., that we are not going to get too deep into in this particular class. So imagine that water has surface tension. Water is like a very thin membrane. It can sort of pulse up and downward like you see with the waves. Assume that you are surrounded every day by this invisible membrane, this electromagnetic field, and that electromagnetic field can pulse up and down with waves just the same way the water can, right? And if you can accept that, then we can move forward. So, you will often hear people refer to light as an electromagnetic wave for that reason. The main difference between this and this is that sound waves, like the kind that you make in water, must have molecules, that the molecule is doing the vibrating. In the electrons that we're about to see, the electron vibrates a little bit, but the pulses it creates are not more vibrating electrons. They are simply an invisible material or invisible film that is vibrating back and forth, for lack of a better word. Okay, so let's talk about waves. You've probably seen waves at the beach or other places that may look something like this. This is a classic wave shape. I'm going to be just giving us some vocabulary that we can use to talk about them, and I'm going to draw right here a dashed line through the center about, and the purpose of this dashed line is I'm going to suggest, if I had drawn this very nicely, that this peak up here is the same distance above that dashed line, and this trough is below that dashed line. So this is supposed to be the midpoint, or the equilibrium point, if you will, of this light wave. And so we're going to identify a couple pieces of this wave. For instance, chemists find it useful to talk about the distance, how tall this wave is above that dashed line. And they use a special word. They use the letter A, and A refers to the amplitude of the wave. Now, we won't go too deep into wave functions here, but the amplitude is, for your purposes, is related to the energy the wave carries. And a better way, or a more practical everyday way to think about that, is the brightness. So amplitude is related to the brightness of the light. So if we have a brighter light shining out of a bulb, we might say that bulb is shining with a bigger amplitude than if we had a weaker bulb or something like that. Okay? It will also be interesting to us and to chemists in general to talk about this distance here. So as these wave peaks travel, let's suppose they're traveling to the right here, they will periodically, you will have these wave peaks passing a certain point, And it is often useful to know how far apart they are from one peak to the next peak, or from one trough to the next trough. Because if this is a uniform wave, then this distance here would be the same as this distance here, for instance. And that distance is a length. So you would think maybe we'll use the letter L for length, but chemists have decided they're going to use the Greek letter L. So Greeks used to write their L's like this. And it's called a Greek letter lambda. What you need to know is it represents the wavelength. Now, why do chemists want to talk about the wavelength? What does it mean? Let's give you a practical way to apply the wavelength. The wavelength you can think of as the color. How does that work? It works like this. So your eye, let's suppose you have an eyeball. Here's your eyeball. Here's the lens at the front and all the pieces that let the light in. And let's suppose a wave comes into your eye like this. Okay? At the back of your eye, right back here, are all these structures, these chemical structures. There's proteins, all right? And proteins are big folded chemicals. Let's say that's one protein, and maybe you have another one that's bigger and more folded, and et cetera, like that. Suppose a length of light comes in that is just the same length as that kind of protein. It can be absorbed by that protein. All right? While a different wavelength comes in that is the same size as that protein, which could be absorbed by this protein. Now, this little tiny wavelength is not big enough to be absorbed by this guy. They have to match. They have to basically fit into each other, if you want to think of it that way. It's a term called resonance. We won't get too deep into it. But this is the right wavelength of light to be absorbed by that protein, and this is the right wavelength of light to be absorbed by that protein, but not vice versa. This guy won't fit here, this guy won't fit there. And you have a bunch of different sizes of proteins in the back of your eye, and we'll talk about that in more detail in a little bit here. So what happens is, let's suppose this little wavelength of light might be a blue wavelength of light. Well, when this protein absorbs it, it sends a message, an electric signal up to your brain through the optic nerve, and says, look, I saw what I'm supposed to see. And the brain says, oh, you're the blue type of protein. That must mean you saw blue light. And that's how we see blue light. Your brain interprets this protein absorbing a light wave as having seen a blue light. Well, maybe this protein here, this big one, is absorbing this size, and maybe that's a red piece of light, a red wavelength. Okay, well, when he vibrates, the brain says, oh yeah, when your big protein vibrates, I'm gonna say I saw red, and it interprets it as red. So that's the signal that your brain is interpreting, is just the different sizes or wavelengths of light that come in. Now, the amplitude has no effect on that, just the wavelength. The amplitude would be the brightness, okay? And it might cause this to absorb a much more energy, and that's how your brain would interpret whether it was a bright blue light or a dim blue light, okay? So you can think about it that way. Regardless of whether it's a little tiny blue light, or a big long red piece of light, or any other color, we find that all of the different colors have the same speed. And we're going to use this letter for speed, that C is the speed of light. And all of them travel this speed, 3 times 10 to the 8th meters per second, no matter what. So if I made a little blue pulse here and a big red pulse here, then after 1 second, they would both have traveled 300 million meters. And that's true of all light, basically in a vacuum. And I have rounded this number. It's 2997 something. But we round it to 3. That's enough for this class. Okay. So no matter what speed you are, no matter what wavelength you are, if you're a light ray, you travel the same speed. We will talk about waves in one more way, which is this. Suppose, and I'll draw two different waves here. Let me draw a long wave. I'll exaggerate it, and a little tiny short wave, right like this. And I want you to picture that my hand here, these rays are traveling towards my hand and going through my hand. But every time one of the peaks hits my hand, it makes a noise. And think about what that would sound like for this big wave as it goes through my hand. You would have a peak, but they would be very far spaced out. So you might hear this. There'd be a lot of space between the hits. Whereas for this very short wave, you might hear. very, very, very frequent hits, okay? And that's actually the term we're going to use, which is the frequency of the wave, okay? And we'll use this term F. So the frequency of the wave is how many of those hits we get per second. So we would say the frequency equals pulses per second, or peaks per second, or however you want to think about that. Think about what I told you earlier about amplitude and how I said it was related to energy. Well, if this wave comes and hits, that amplitude maybe hits like this. Not very frequently. This little wave hits very frequently. And so I am probably going to absorb more energy from I say the little wave. Let's assume that I drew them at the same height as well, because you don't have to have small heights. Let's suppose they are both the same amplitude. But if I get more peaks per second from the lower or the higher frequency wave, then I will absorb more energy. And there is an equation for this, which we will probably not solve in this class, but I give it to you anyway, that the energy associated with waves is equal to some number h. If you want it, it's 6.626 times 10 to the minus 26. It's a very small number, but it is a number, times the frequency. The energy is getting bigger when the frequency gets bigger. Okay? And that will help us understand what I'm about to draw. So, in the world of light, there are many, many, many more frequencies of light that we cannot see than there are frequencies that we can see. So here's your eye, and there's your lens. You can imagine that waves that are this big can make it through your eye, and there are certain size structures at the back of your eye, but if the wave is too big, you will not have a structure at the back of your eye that is sufficiently shaped or vibrates at the right frequency to absorb it. So right now, there are waves passing through the room that you cannot see. They are invisible to you. There are light colors that you cannot see simply because they are the wrong size. And your biology hasn't developed, your body has not developed eye structures that are sensitive to those frequencies. So let's go on a little journey here. We're going to start with very long waves, and then we're going to go to little short waves, and a little shorter, and a little shorter, and a little shorter, like that. And I didn't mean to draw them smaller amplitude as I went to the right. That's a bad habit I have. But these are definitely longer peak to peak, and these are definitely shorter peak to peak. So I'm going to start with the biggest waves we know about, which are called radio waves. Radio waves are very long. How long, you might ask? They're probably the length of our school. Some radio waves are upwards of 100 meters long, maybe even 1,000, all right? I think they're even 10 to the fourth if you go to the upper end. So radio waves are very, very, very long, much too big to fit in your eye. So you cannot see them. When I think of radio waves, I think of those big radio towers. Like you see outside of broadcasting stations, like that. Some of those are hundreds of meters tall. And I think about electricity passing up and down in that tower, and I think about a wave that is literally as long as that tower, because maybe that's how they generate it. Okay? A radio tower doesn't play sound waves. When we think of the radio, we think of the sounds, the songs that we hear over our device in our car, which we call a radio. But imagine the radio was a big speaker and it just blasted sound waves. Then no matter where you went, you would always hear every single radio station. It would be noise all the time. That would be terrible. So what they do is they shine out light waves, very long light waves. And your car has a little circuit in it. It's actually a capacitor circuit, in case you wanted to see. But it has a little electric circuit in it. And that circuit can be tuned. You can adjust it with that knob to vibrate at different frequencies. And what you do when you tune it is you get it to vibrate at the same frequency as that light wave that the radio tower is shining out, because each radio tower purchases a certain frequency that only they are allowed to shine out that frequency light, which means that they get to send their messages. Now that light is a code. All right. And so when your car uses that circuit, it absorbs that light, just like the structures in your eye can absorb the light. We can tune this to absorb very long wavelengths of light. And when we do, we absorb that light in, and then we are allowed, then our circuit in our car decodes it and tells you, play this music. And the speaker says, okay, I'll play that music. And that's how we do. So we're just shining light across the valley from these radio stations. And when you want to be able to hear the message that light is portraying, you absorb it into your car's radio, and it turns that into code and tells the speakers what to play. Then, as we get smaller, we go to like microwaves is the next one down. Now, micro sounds small, but it's actually a very much bigger than your eye could absorb. We think about that device like the microwave in your home. The microwave in your home sends out these waves that happen to vibrate at the same frequency that water vibrates at. And so just like the structures in your eye, the water can absorb it. But when the water absorbs it, it gets hot and it cooks your food. So what you do is you take a little box, you put your food in the box, and then it shines the light on your food. And because they both vibrate at the same frequency, the water and most of the food we eat contains water, it can get hot. It can absorb the energy from the light. So all you're doing to cook food in a microwave is shining light on it. Another way we use microwaves is with cell phones. So like the radio tower sends out radio waves, your cell phone sends out microwaves. So anytime you want to send a message, you type it into your phone, it will send out a microwave frequency to the nearest tower, and it will send out that microwave frequency to all the other phones. And if it's the phone you had intended it to get, it will take in that frequency and turn it back into a message. So we're just shining light back and forth when we call each other on our cell phones. When we get past micro, we get to a length of light called the IR, which stands for infrared. Infrared are shorter wavelengths than micro, than radio, but they are still too big to fit into your eye. Now, this is a type of light that vibrates at the same frequency that a lot of our body molecules vibrate at. And so it's often referred to as a heat ray. Now, that's not entirely accurate. It's a light ray, but because it vibrates at the same frequency as your body molecules, like the molecules in my hand, let's say, if I put my hand in front of an infrared light, these molecules can absorb that light very easily because they tend to vibrate at the same frequency, and so my hand would get hot. Likewise, when my hand gets hot and my molecules start to move around more, they can vibrate and send out their own infrared rays. So it is associated with heat, but really it's because of the molecular motion of biological molecules that tends to generate this type of radiation or absorb this type of radiation. Now, you can't see probably very much into the infrared spectrum, if at all, but there are certain animals, particularly animals that hunt at night, who have evolved structures in their eye that are large enough to absorb this kind of radiation, because it's very useful if you are at night and you can't see anything but heat because there's no sunlight. Then you can see all the little animals that you might want to hunt because their bodies, their molecules are vibrating in this frequency range and giving off this type of light. Next, there's a very little chunk here. And this is the chunk of light that is just the right size for our eye to see. I'm going to expand it out a little so we can see it. It's the visible section, so I'll call it visible light. And on the big end, so we're getting bigger to smaller as we go left to right, the largest light we can see is red light. And then it's orange light, and then it's yellow light, and then it's green light, and then it's blue light, indigo, and violet. Violet is the shortest wavelength. We still have eye structures that can absorb it. Roy G. Biv, you may remember that from previous science classes. Big light or big wavelength, small wavelength here. Low frequency, right? The bigger the wavelengths hit my hand at a lower frequency, the smaller stuff, higher frequency, okay? And as we go from big to small and we go to lower wavelengths, we also go to higher energy. Remember, we talked about that energy is related to the frequency. So these high frequency waves have more energy. And the way I remember the order here is that Darth Vader always loses to Luke Skywalker. Now, the reason Darth Vader loses to Luke Skywalker is Darth Vader's lightsaber is red. but Skywalker's lightsaber is blue. So it has a smaller wavelength, a higher frequency, which means it has more energy. So Luke won because he had more energy. That is a joke, but maybe if it helps you remember, use it. As we go past the visible light, past violet, we get into smaller stuff that now we can't see because it's too small. This side we couldn't see because it was too big. This side we can't see because it's too small. And right next to violet we have ultraviolet. And you'll see naming conventions, right? The infrared is too big. It's much bigger than red. The ultraviolet is smaller than violet. In sound waves, we have similar terms, like ultrasonic are sound waves that are too small to be heard by your ear, whereas infrasonic are too high-pitched to be heard by your ear. So dog whistles are infrasonic waves. I may have that backwards. I don't think so. Anyhow, ultraviolet are much smaller than visible light, and yet they carry way more energy. You could probably, right now, my hand is sitting underneath regular old visible light. And regular old visible light has less energy, and I could be here all day and I will not get a tan. But if I go out to the beach where there's a lot of ultraviolet light from the sun and the building isn't blocking that ultraviolet light, I can get red very quickly, okay, because that has way more energy. So this starts to become dangerous as we get into the ultraviolet range. Okay, we sometimes refer to this as ionizing radiation, because it can rip off electrons. Okay, as we keep going, smaller than ultraviolet, we have X-rays. I actually have a dentist appointment later today that I'm going to go to, and they're probably going to X-ray my teeth. X-rays are so small, they can actually fit between the molecules of my skin. So if you've ever done this, if you've ever put your hand up and you make a shadow puppet with your hand on the wall, right? And it makes that shadow. You can't see it very well here because of the lighting in the room. What's happening is the visible light is hitting your hand, but it can't get through. And so what you see is the lack of light hitting the wall. For an X-ray, they shine a light through my hand, but the light is so small, my skin can't block it, but my bones can. And so what I'm getting is the shadow of my bones on a piece of film, and then they develop it. Actually, they leave it as a negative. So what you see is the whiteness instead of the darkness, but it's still, you can think of it as a shadow. And so when I go in for my X-rays for my teeth today, they're going to put a big, heavy film behind my teeth and shine a light through my face. My skin won't stop the light, but the teeth will, because they're very dense. And this kind of light can get through not dense stuff like skin, but it can't get through dense stuff like bone. It's also much more energy than the ultraviolet because it's much smaller and higher frequency. So with X-rays, I remember seeing videos in my physics class when I was your age where they would show a lady playing the violin and her hand was moving back and forth like this, but they had taken the film with an X-ray camera, and so what you saw were the bones of her hand going back and forth like this. You could see her skeleton playing the violin. Now, it was very useful for learning about functions of muscles or not muscles, but bone structure and things like that. But it was also very dangerous, and some of these people developed cancers and things because they're being hit with some very high ionizing radiation. So if you ever go to the dentist, you'll notice he puts a big heavy coat, a big apron on you, and that's filled with lead and coated in leather so that the radiation doesn't get to all of your body organs. It just gets to your teeth, hopefully. And then he leaves the room, or she leaves the room, because if he or she has 20, 30 patients a day and gives X-rays all day long for all of their lives, that dentist would be absorbing a lot of X-rays, and that's not safe. Okay, so we want to limit our exposure to these as much as possible. One little quick, film picture with an X-ray that doesn't take hardly any time is not a large exposure to X-rays, and probably not over your lifetime going to be very dangerous. But if you were to sit under an X-ray light for several hours a day, that could be quite dangerous. It could add up. And the smallest ones we will talk about, which is the smallest that we have identified, are gamma. When I say we, I mean scientists. So the very smallest rays out there are gamma rays. They are super high energy. They are not like going to turn you into the Hulk. If you were to sit under a gamma light bulb that was sufficient intensity, it would probably just melt your brain and you would die. That's very grim. But they are very dangerous. So we try to limit gamma exposure as much as possible. It's so small, it can pass through metal, it can pass through bone, it can be absorbed by those things as well. But when I was a student at UC Irvine, we worked in Roland Hall was the name of our building. And I took a radioisotopes class where we were dealing with radioactive chemicals. They had a nuclear reactor. So there's this large, I'll just draw it as a block, but it didn't quite look like this, block of uranium. And to protect people from the gamma radiation, they had it at the bottom of a 25-foot pool of water. And it needed that much water to block all of this dangerous radiation, these light rays that were coming off of it. Okay, so these are all different types of light rays. And we'll start with this understanding. Now, as we go forward, let's talk about how we determine that light is a wave in the first place, because for a long time, there were scientists out there that said, well, we can see light, we can tell it's there. Is it actually a wave? Because we can't see the ripples on like on a pond. How do we prove that? So here's a water experiment that we can do. Let's suppose we had a tank of water like this, and I make some ripples in it. And I have a wall here. This is a wall where I've cut 2 holes in the wall. And those ripples go outward. What happens is as the ripples approach this, they'll get sliced up, right? They go out like this. And only a little portion of the ripple will actually make it through that gap. And as it goes through the gap, it'll start to radiate outwards and get bigger. And at certain points, they will overlap. Now, if you've ever been to the beach, what you find is that those points where waves come in and slam into each other, they actually get bigger. They get more intense. And so any point of overlap would create a bigger wave. And what we tend to see is like big waves would hit here, and big waves would hit here, and big waves would hit here. Okay? Well, the opposite is true when a big wave hits a trough. When a big wave hits a trough, it kind of cancels out. And so you would get spots when these waves hit the wall of high amplitude peaks hitting where the 2 waves overlap constructively, and you would get spots where they don't. That's with water waves. So some clever scientists said, well, let me try that with a light ray. Let me shine a light ray. Let's say that's my light beam. And I'm going to take a card, and I'm going to cut 2 lines into the card. I'm going to cut 2 little holes in the card. So picture those 2 lines I draw like little holes. And when the light went through, it split into peaks just like if it had been a water wave. So he said, that kind of has to be proof that this light is behaving as a wave. Okay. One other interesting thing he found, though, is that we talked about light comes in all different sizes. And red is a big wave, and blue is a small wave, and violet is a small wave. So one other thing that happened when the light split is that what you got were like dots here that were rainbow dots. So you would get the red here, and the orange here, and the yellow here, etc. Because of their different sizes, they weren't overlapping in the same spot. You can think of this as the wavelength, right? But each of those different kinds of light came in a different size. And so it overlapped at a different spot on the wall. So if you ever looked out at clouds, like a storm that's dripping water, but the sun is like over here, maybe the clouds don't cover the sun, and the sunlight shines through some of that water, and you're standing over here, it will actually split the light, and you'll see this lovely rainbow of different colors. The reason you're seeing that is the same reason that light splits when it goes through these 2 gratings, okay? Because each of those different pieces of light will overlap constructively at a different point. All right, and actually the rainbow effect is a prism effect through the cloud, whereas it's a diffraction effect here. But the argument behind it is all of those little colors of light will show up in different spots because they are different lengths or different frequencies. And so this was the argument. Hey, we're dealing with waves here. So let's take that And these other scientists said, well, let's try something else, because what we're seeing here, when you see light coming out of a bulb, here's a bulb, like you have in your ceiling. That light is all the light at once. It's red and green and blue, and when you get all the light together at once, you get what we refer to as white light. Okay, so white equals all colors. And that's why when you put a prism in front of it, or when you put a diffraction grating in front of it, you can split it into its individual colors. And you can see the red lining up over here, and the yellow lining up over here, and the blue lining up over here. So they said, well, let's try this with a different kind of bulb. I'm going to take a tube of glass, and I'm going to put a metal cap on this end and a metal cap on this end. And I'm going to suck all the air out of it so there's no air. And I'm going to fill it with, let's put in there some hydrogen gas. Not much, but a little bit of hydrogen gas. And then I'm going to connect it to a battery. That's a symbol for a battery. And I'm going to put electricity through that tube. What it does is it makes the electrons in the hydrogen vibrate. And they vibrate very quickly, and they make light waves. Okay? And so light comes out of it. It doesn't look like white light, though. So what we do is we take the light waves that are coming out of it, and we take our card with our two slits, and we split them. And what comes out the other side is not this nice continuous rainbow, right? The rainbows you've looked at probably are solid all the way from red to violet. What we see is a red line, and a yellow line, and a green line, and maybe a violet line, all spaced out, just single lines, instead of the whole rainbow, instead of the whole spectrum, we might say. A spectrum is all of it. This spectrum for hydrogen is very truncated. It's missing pieces. And they try it with helium. And when they try it with helium, they get lines like this, but they get them in different spots. And every single atom that they try to put the electricity through, when they shine the light through a grating and catch all the pieces of light, they get different, scientists that is, they will see different individual lines, but that's all they see for a unique atom is individual lines. Okay, so how do we interpret this? Well, Niels Bohr is one of the scientists who worked on this, and he came up with a theory. He said, what if, here's your atom, here's your nucleus. I'll just draw a couple of for hydrogen, the nucleus only has one proton, so we can do that easy. Here's the nucleus of hydrogen. And here's the electron for hydrogen. Suppose that electron is orbiting that nucleus like this. And that's an energy state. It has a certain amount of energy. And then suppose that it could be orbiting out here or out here. But that it cannot be orbiting right there in between. I'll draw a dashed line. That dashed line is off limits. It cannot go there. And it can't go anywhere in between those lines. It could be here, it could be here, it could be here, but it can't be anywhere else. He said, if we pass electricity through it, if we connect it to the battery, that electricity is going to give this electron energy. And when it does that, it'll go up to there. The only place it could be other than here is one of these other rings. It can't be somewhere in between. And if it loses that energy, it'll fall right back down. And it can vibrate back and forth between those two rings. Well, if it were to vibrate between these two rings, that would give you a light ray about that, let's say that light ray right there, associated with that energy level. If it went back and forth, let's suppose it jumped here, because it could also be at that ring, and then fell back from that ring. Well, that transition might be a light ray of that size. And what if there was a third energy level that it could go at, and it could go back and forth from there to there? So his proposal was that the reason we are seeing only certain frequencies of light, right? These are all different frequencies. Well, those are all also different energies. That must mean that it's vibrating back and forth between very specific energy levels, but not all of the energy levels. It can't go from here to here, right? Because if it could do all of the energy levels, we would see all of the different kinds of light when it vibrated back and forth. This idea that electrons have specific energy and not all of the energy, they have a specific quantity of energy that they can have, not any quantity of energy that they could that could possibly exist, is the basis for what we call quantum theory. And it's just that's all it is that instead of having all of the spectrum available, we have specific energy levels available. When we say that word quantity, that's where this word quantum comes from. We have specific quantities of energy. We might say a quantum of energy is used to get back and forth between those two energy levels. So if you've ever heard someone say quantum theory and thought it sounded high level, there's a lot of high level math behind it, but the concept is just discrete energy levels as opposed to spectra. Okay? And that's how we identify all of or how we understand some of these atoms. For instance, originally, you can do this with any light. You can put up this sort of card, this sort of filter, diffraction grating, and catch any light you want, and you can look at the lines of light, the types of lines, and if that light was generated by an excited hydrogen atom, you would definitely see those 4 lines. And if it also, maybe you had a sample of multiple gases, it also had some other gases in there, you might see other lines from those other gases, okay? That's how we kind of tell things apart. Well, excited scientists said, hey, let's do this. The sun is giving off lots of light. Let's catch it and put it through our card and catch all the little lines that come off of it, and let's look through those lines and see what elements we can see in that star. This is the sun, right? What elements make up our sun? This is the first time we had a way to deal with or to find evidence for different chemicals that might make up our sun. And they found a weird pattern. They found a set of lines. They found hydrogen. There's a lot of hydrogen in our sun, and they found other metals and things. But they found a set of lines that didn't match any known chemical on Earth. They said, wow, we just found a new element that only exists in the sun. And what they did was, if you remember your Greek mythology, the Greeks thought, or made up a story rather, of a dude in a chariot, and he drove the flaming sun across the sky. The sun was a bunch of flaming horses, and his name was Helios. Well, they decided to name this element that they thought only existed in the sun, they named it helium. Now, since then, we have been able to discover and isolate helium here on Earth, and it's very hard to find, namely because it doesn't bond with any other element, so there were no helium compounds, right? It's a noble gas, and we'll talk about why that happens. But that was the first time we had ever seen it, and we figured it out because of the light that came from its atoms' electrons. Okay, so hopefully that was useful to you.